Good morning, students. I'm Chaitanya, Assistant Professor in Mathematics, working in Institute of Aeronautical Engineering, located at Dundigal, Hyderabad. Today, I'm going to discuss on the concept of minimum variance unbiased estimator, which is a part of fourth module, maximum likelihood parameter estimation, and let us look into the details. Actually, we have started this chapter. In this chapter, we have begun our search for good estimators of unknown deterministic parameters. That means, in maximum likelihood estimation, in this chapter, we always wish for a good estimator, and we always try to maximize the value of the estimator or the parameters of the probabilistic distribution. We will restrict our attention to estimators which on the average yield the true parameter value. That means our parameters are said to be good when they are consistently yielding on an average very accurate value of the parameter theta. That means when we call theta cap is a good estimator, means it should on an average, that means expectation of theta cap should be equals to theta. That means on an average it should give consistently good series of values or consistently good estimations of theta. Okay. Within this class of estimators, the goal will be to find the one that exhibits least variability. So there might be several estimators which are unbiased estimators of theta, and among them to guess which is better, we must need one more verification criteria, that is called variance of theta cap. Okay, that means least variability means with the help of variance of theta cap we'll come to judge which one is the best estimator. Okay, the estimator thus obtained will produce values close to the true value most of the time. So in this way, if we check that the consistency of the estimator is almost as the original parameter, that means on an average the estimator value will be almost in and around the parameter, and the variance is least when compared to the other parameters, then we call that estimator as a very, very good estimator. Okay, the notion of minimum variance unbiased estimator is examined within this. So by combining these two, we have the notion of minimum variance unbiased estimator. Okay, now what do you mean by unbiased estimator? Let us have a look into this. An estimator theta 1 is said to be unbiased estimator of theta if we call if expectation of theta 1 is equal to theta. That means unbiased estimator means if the formula, suppose this is a population and we are trying to estimate theta based on the sample available data, and this theta cap is said to be an unbiased estimator of theta if expectation of theta cap is always equals to theta. Okay, since the parameter value may in general be anywhere in the interval, unbiasedness asserts that no matter what the true value of mu or theta, okay, our estimator will yield it on the average. That means irrespective of the sample size we are taking, our estimator expectation of the estimation formula will be equal to the theta. Then we call it as unbiased estimator. If expectation of theta cap is not equals to theta, we call it as biased estimator. Sometimes it may be less than theta, or expectation of theta cap may be greater than theta. Okay, When expectation of theta cap is less than theta, we call it as negatively biased estimator, and when expectation of theta cap is greater than theta, we call it as positively biased estimator. Estimator is unbiased does not necessarily mean that it is a good estimator. Just merely expectation of theta cap being equals to theta doesn't mean that it is an unbiased estimator. We need more support. Good estimator. We need more support statistically in order to make it as a very good estimator. It only guarantees that on the average, it attains the true value. That means on an average, it attains true value, but it is not sufficient to say that it is a very good estimator. So a persistent bias will always result in a poor estimator. That means if expectation of theta cap is not equals to theta, then definitely it results into a poor estimation. That means we may not be able to estimate the population missing values or missing features of the data set correctly. So unbiased property has an important implication when several estimators are combined. A reasonable procedure to combine these estimates into a better one by averaging them to form is unbiased estimator. That means a reasonable procedure to combine these estimates into a better one by averaging them to form an unbiased estimation of population parameter. Okay, population parameter. Now, if you see this, for an estimator to be unbiased, we mean that on the average, the estimator will yield the true value of the unknown parameter. Since the parameter value may in general be anywhere in the interval, okay, and unbiasedness assets no matter what the truth value of theta, our estimator will yield on the average. That means E of theta cap is equal to theta, irrespective of the interval, irrespective of the domain, we'll have this. Then we call theta cap is the unbiased estimate of theta. Okay. Here we are seeing a random variable function defined on a finite set of natural numbers. See, x of n is a random variable function which is defined on finite set of naturals 0, 1, 2, so on n minus 1. Okay, it is defined as x of n is equal to a plus w of n. X of n is equal to a plus w of n, where a is the parameter to be estimated and w of n is nothing but small error which is permissible. That means job of x of n is to estimate a. Okay, then there might be some bias or some error that is called w of n. Okay, then what is the reasonable estimator of x of n in estimating a is defined like this. A cap is equal to 1 by n summation n is equal to 0 to n minus 1 x of n. Okay, or we can simply say it as sample mean. Because we are adding n observations and dividing with n, that is why we can call it as sample mean. So what it says, sample mean is always an unbiased estimator of the population mean. Okay, now let us take this. Let us check whether it is true or not. Let's start with a cap. Expectation of a cap is equal to expectation of 1 by n summation n is equal to 0 to n minus 1 x of n. 1 by n comes out, it would be summation n is equal to 0 to n minus 1 expectation of x of n. Okay, and 1 by n comes out, this expectation will be nothing but a. So a plus a plus a, so on a n times. That means 1 by n into na, that is equal to a. So here expectation of a cap is a. So that means a cap is unbiased estimator of a. Okay. So this is in this example we have obtained an unbiased estimator of A, which is nothing but A cap, which is nothing but the sample mean. So with this, what we have proven, sample mean is an unbiased estimator of population mean. Okay. Now, just like this, if we see that we are taking another parameter, another estimator called A reverse cap. A reverse cap is defined as 1 by 2n into summation n is equal to 0 to n minus 1 x of n. In this case, we observe that expectation of A reverse cap is not A instead of it is A by 2. So because it is not equals to A, we cannot treat this A reverse cap as unbiased estimator of A. Okay. So it is a biased estimator of A. An estimator is unbiased does not necessarily mean that it is a good estimator. It only guarantees that on the average it will attain the true value. That means if expectation of theta cap is equal to theta, we cannot say that this is a better or good, very good estimator. It just guarantees that it is consistently going towards theta. So it is up to some extent it is good, but we need one more supporting criteria, which is called efficiency. Basing on the variance, we calculate the efficiency, and the efficiency decides whether the estimator is perfect or not. A persistent bias will always be result in a poor estimator. As an example, the unbiased property has an important implication when several estimators are combined. A reasonable procedure is to combine these estimates into a better one by averaging them to form. That means when we have a set of unbiased estimators, say theta 1, theta 2, say theta k of theta, a better way of obtaining a more elegant estimator is just averaging them. That means theta 1, theta 2 is theta k by k will be again unbiased estimator of theta, and it acts more efficient than these parameters. Even though these are all unbiased, this average becomes more unbiased as well as efficient than these parameters, the estimators. Okay. Assuming the estimators are unbiased with the same variance and uncorrelated with each other, expectation of theta cap is equal to theta, and variance of theta cap is equal to variance of one by n into summation theta I is equal to 1 to n. That is equal to 1 by n square summation I is equal to 1 to n variance of theta I. 1 by n square summation I is equal to 1 to n. Variance of theta I is nothing but variance of theta I nothing but variance of normal variance, population variance, that is variance of theta. Okay, theta 1 cap you can understand in general, and this is n times, means it becomes n into 1 by n square into n into variance of theta 1. So when n and this cancels, we get variance of theta 1 cap by n. That means we are clearly showing that theta cap is not an unbiased estimator of theta. That means the sample variance cannot be directly an unbiased estimator of the population variance. So in these results, we observed that sample mean is an unbiased estimator of population mean, and sample variance is not an unbiased estimator of population's variance. Okay, so sample mean is an unbiased estimator of population mean, But sample variance is not an unbiased estimator of population variance. Now, so that is what I have written. Sample mean is always an unbiased estimator of population variance, but the sample variance is not an unbiased estimator of population variance. Now, suppose we have an estimator theta cap of population parameter theta, and we understood, or we came to know that expectation of theta cap is not equals to theta, and expectation of theta cap is equals to theta plus b of theta. That means the difference between these two is called as b of theta, that is bias of theta, okay, due to theta cap. Then this b of theta is called bias of the estimator theta cap. So how we define bias of the estimator theta cap? Nothing but bias of the estimator theta cap is nothing but expectation of, suppose when expectation of theta cap is not equals to theta, there will be some difference, and that difference, the absolute value of the difference, that is the mod of e of not need not be, it is mod, the difference between the expectation of theta cap and theta is defined as bias of theta. Okay, bias of theta. And if this bias is positive, we call that theta cap is a positively biased estimator, and if this is less than 0, we call it as negatively biased estimator. So here, when we are estimating the population parameter theta cap, here we are observing that this theta is centered, that means equally, it is concentrated about the mean, and here also we are observing that the theta is the theta distribution is centered is symmetric about this line. This is symmetric about this line, and here also the data has been symmetric about the center line. But here that means both theta 1 or theta 1 cap and theta 2 cap both are unbiased. That means E of theta 1 cap is equal to theta, E of theta 2 cap is equals to theta. Both theta 1 cap and theta 2 cap are unbiased estimators of theta. That is what we are observing here. Okay. Now, here, but what the difference, that means both are good estimators. That means the expectation of theta 1 is equals to theta and expectation of theta 2 is equal to theta. How to determine which is better, which is the better estimator? So there lies the problem. You see here, this even though the data is being symmetric about the center line, here also that it is symmetric about the line, center line. Here you are observing that the spread from the center to the right wing and center to the left wing, and if you take this spread towards right and left, the spread is more here but the spread is less here. That means this is more efficient than, because it is taking less space to cover all the data points, but here we have to allocate lot of space to store the data, but here within less space, less spread, the data has been spread in a very less range equally on either side of the center line. So this is called most efficient. Okay, so if you take the biased estimator, see here this theta is not falling in the not falling in and around the center line. It is very if you take this, the left side is more area and the right side is less area. This is called biased or negatively biased. If you take here, completely theta is out. That means here also you can see that the left side is more area and the right side no area. This is also biased estimator. That means when estimator is biased, you will find to left side of theta you'll have more area, or right side of theta you'll have more area. But in unbiased estimator you'll see that on either side of the theta you'll have equal areas. So minimum variance criteria. Mean square error MSE is defined as MSE of theta cap is equal to expectation of theta cap minus theta whole square. MSE of theta cap is equal to expectation of theta cap minus theta whole square. That means if you take theta cap minus theta as x, the expectation of x square you defined as summation x square into p of x, or integration into x into p f of x dx, x square into f of x dx. So now we are defining the mean square error is nothing but expectation of theta cap minus theta whole square. Unfortunately, adoption of this natural criteria leads to unrealizable estimators, ones that cannot be written solely as a function of the data. Okay, in searching for optimal estimators, we need to adopt some of optimality criteria. To understand the problem which arises, we first rewrite the MSE as MSE theta cap is equal to expectation of theta cap minus, that means what is MSE? It is nothing but expectation of theta cap minus theta whole square. Expectation of theta cap. Now I am adding and subtracting the expectation of theta cap. Okay, that means adding and subtracting expectation of theta cap. It becomes like this. Now E of, so this whole square is for whole thing, that means E of x plus 5 whole square. So when you look at this expectation of theta cap, that means if you expand this, that means E of I'd like to write it here. For this step, if you expand, treat it as A, treat it as B, A plus B whole square, that means expectation of A square plus expectation of B square plus 2 into expectation of AB. What is expectation of AB? 2 into expectation of theta cap minus expectation of theta cap into expectation of theta cap minus theta. Okay, then this is when you expand this entire term becomes 0. That means we remind, that means this becomes 0. We'll be remind with expectation of A square plus expectation of B square. That means expectation of A square is equal to expectation of theta cap minus expectation of theta cap whole square plus expectation of theta cap minus theta whole square. Okay, we'll be reminded with these two things. Now A square plus B square we have written, but what is this? This is nothing but it is nothing but x minus mu whole square, expectation of x. That is nothing but variance of x. We have this second definition in our mind, which is expectation of x minus mu whole square is equal to variance of x, and hence variance of x means we have this is equal to variance of theta cap plus this is nothing but bias of theta cap whole square. So what we have observed, the mean square error of theta cap is nothing but variance of theta cap plus bias square. This is always non-negative, this is always negative, so that we understand that MSE is always non-negative or greater than or equal to 0. So we obtained an interesting relation between MSE of theta cap and the variance of theta cap and the bias of theta cap. That is, we have proven that MSE of theta cap is nothing but variance of theta cap plus bias of theta cap whole square. Okay, for this we have started with the MSE definition. and we have expanded a, this is a, this is b, a plus b whole square. We have expanded expectation of a square plus expectation of b square plus 2 into expectation of ab. And when we expand expectation of a square plus expectation of b square plus 2 into expectation of ab, you observe that this becomes 0 by cancelling the terms. Okay, that means 2 into expectation of a into b, that means 2 into expectation of this into expectation of this becomes 0. So we'll be remained with only these two things, expectation of a square plus expectation of b square. And this is nothing but variance, and this is nothing but expectation of b square can be understood because it is already expectation of a constant. It could be understood as expectation of some c whole square. It looks like, that means this is the c. So this is the c square. It looks like c square means this is nothing but the bias. So variance of theta cap plus bias whole square. So in this way we can understand the mean square error. Now an alternative approach is to constrain the bias to be 0 and find the estimator which minimizes the variance. So what is minimum variance criteria focuses on? It focuses always on to make the bias 0. That means to make expectation of theta cap not equals to theta. So the bias is nothing but bias of theta cap is nothing but the difference between expectation of theta cap minus theta. So how to tend to this 0? So what is the criteria in order to make that the bias is almost 0? So that for that we will use a criteria which is called minimum variance unbiased estimator criteria. By using this estimator criteria, we come to know that whether theta cap, bias of theta cap is almost 0 or not, is tending to 0 or not. Okay. If b of theta cap is equals to 0, we call this as minimum variance unbiased estimator. So we are defining what is minimum variance unbiased estimator. Minimum variance unbiased estimator means first of all, theta cap is said to be minimum variance unbiased estimator, okay, MVUE of theta if first expectation of theta cap is equal to theta. Second thing, b of theta that is equal to the expectation of theta cap minus theta is equal to 0. So if these two happens, we call theta cap is minimum variance unbiased estimator of theta. Okay. The estimation error will therefore be less likely to be large. So always this error will be for minimum variance unbiased estimator, this will be almost 0 or very small value. Okay. Here he is giving one example where there are two independent random variables x of 0, x of 1, whose density functions are given that x of 0 follows normal distribution with mean theta, which is to be estimated, and variance 1. X of 1 follows normal distribution with mean theta and variance 1 when theta is positive, and mean theta variance 2 when theta is negative. Now we are constructing two estimators called theta 1 as half of x of 0 plus x of 1 by 2. And we are constructing one more estimator theta 2 as 2 by 3 of x of 0 plus 1 by 3 of x of 1. Okay. Now we'll verify which one will be the unbiased, whether both of them will be unbiased or not, and which one will be the minimum variance unbiased. Okay. Now let us check. E of theta 1 is equal to 1 by 2 into E of x of 0 plus E of x of 1. But x of 0 is nothing but mean is theta. So half theta plus x of 1, when it is positive, it would be theta, and negative is also theta. So it is theta plus theta. That means 2 theta by 2, that is equal to theta. So expectation of theta 1 is equal to 2 theta. So theta 1 is unbiased estimator of theta. Okay. Now theta 2 cap. Theta 2 cap, if you take and apply expectation 2 by 3 into expectation of x of 0 plus 1 by 3 into expectation of x of 1. Okay, here 2 by 3 into expectation of x of 0 means the mean is theta, plus expectation of x of 1 means the mean, again it is theta. That is equal to its theta. So expectation of theta 2 cap is also theta, and hence theta 2 cap is also unbiased estimator of theta. Okay, it is also unbiased estimator of theta. So what we have proven, we initially proven that theta 1 cap comma theta 2 cap are unbiased estimators of theta. Now we will verify which is minimum variance unbiased estimator of theta. So if we calculate variance of theta 1, that means V of theta 1, which is nothing but 1 by 2 comes outside, that means variance of 1 by 2 into x of 0 plus 1 by 2 into x of 1, right? When a number comes out of the variance, it becomes square. So 1 by 4 variance of x of 0 plus 1 by 2 into variance of x of 1. 1 by 4 into what is x of variance of x naught, that is, see, you can check here, the variance is 1. So this will be 1 plus here 1 by 2 comes out, becomes square. 1 by 4 into what is variance of x1? See here, when it is positive it is 1, and when it is negative it is 2. So when it is positive it is 1, and when it is negative it is 2. So we can write it as 1 by 2, and here 1 by 4, when it is negative, 1 by 4 plus 1 by 4 into 2, that is equal to 1 by 4 plus 1 by 2, that means 3. 1 by 2 plus 1 by 4 means 3 by 4. So here this is what we have observed. Now if you calculate variance of theta 2, it would be variance of theta 2 cap, it would be 20 by 36 and 24 by 36. If you calculate in the same way, you will get variance of theta 2 cap will be 20 by 36 and 24 by 36 when theta is positive and theta is negative. That means when you observe here, this value, of course, it is nothing but 1 by 2 we calculated. 1 by 2 is scaled to 36, and this is 3 by 4, it is scaled to 27 by 36. In the same way, if we calculate for this, like for this, that means variance of theta 2 is equal to 2 by 3 into 2 by 3 comes out, it becomes 4 by 9 into variance of x0 plus 1 by 3 comes out, variance of x of 1. 4 by 9 into what is variance of x of 0? Variance of x of 0 is nothing but here what? When theta is negative it is 2, when theta is positive it is 1. So we can treat it as x of 0 is 1. So 1 plus x of 1 is 1 by 9 into 1 when theta is positive, and 4 by 9 into 1 plus 1 by 9 into 2 when theta is negative. That is equal to 5 by 9 and 6 by 9. That means when theta is positive and theta is negative. That means 25 by 36, 36, 25 by 36, 24 by 36. By looking at this, yes, it's so sorry, 4 5s are 20 by 36, 24 by this. So what we have observed, this is less than this, this is less than this. Sorry, 18 by 36 is less than 20 by 36 when theta is positive, but 27 by 36 is not less than 24 by 36 if theta is less than 0. So here we can say that both variances are more or less same. So both are, you can say that both are minimum variance unbiased estimators. Okay, and you can see the graph of like this, where we have plotted these two. These dotted lines gives the second parameter theta 2 cap, and the dark line gives theta 1 cap. The CRLB allows us to determine for any unbiased estimator the variance must be greater than or equal to a given value. If an estimator exists whose variance equals to CRLB for each value of theta, then estimate. So CRLB here, Kramer's law lower bound, is a best criteria in order to determine whether MVUE, the unbiased estimator, is minimum variance or not. Okay. For any unbiased estimator, the variance must be greater than or equal to the given value. So when we recap our CRLB, tells that variance of theta cap will be greater than or equal to 1 by Fisher's information of theta cap. Okay, so this gives us a lower bound of MVUE estimate. So CRLB will be used to estimate the lower bound of minimum variance unbiased estimate. Okay. So here you can see that. Here you can see this is CRLB, variance of theta cap is equal to minimum this, and this will be the nothing but expectation of this. Okay, so and so this here you can see variance of theta cap is always greater than or equal to the sample mean. That means variance of theta cap is always greater than or equal to sigma square by n. That means variance of x bar is equals to sigma square by n. We know that. That means x bar is not an efficient, but its variance will be sigma square by n. That we know that in our estimation theory we came across this. Okay, so here we have started with the normal distribution function, and we are trying to calculate. We are going to see an example of Kramer's law lower bound of the parameter A, that is mu, population mean of normal distribution. So here we are considering the product of n normally distributed random variables. We can observe that when we take this product, that means you know that e power x into e power y is equal to e power x plus y, that we are using here, e power x plus y, that we are using here, we get this expectation of x minus mu whole square summation x is equal to 0, 10 minus 1. So we get this, and if we differentiate on both sides, with a, differentiate both sides with a. Okay, what we get 1 by 2 pi sigma square whole power n by 2, and here if you differentiate with a, the chain rule, it becomes minus 1 by 2 sigma square. Sorry, exponential means e power ax integral derivative, that means minus 1 by 2 sigma square e power minus 1 by 2 sigma square into x of n summation minus a whole square Okay, inside derivative with respect to A is -1. So this is the one. So when we differentiate with respect to A, we are applying log. First we have to apply log. Let us redo it. So we are applying log on both sides. LNP log on both sides. Log m, log mn. So log m plus log n. Okay, log m plus log n. Okay. See, when we differentiate with respect to A on both sides, differentiate with respect to A on both sides, we get this is 0 plus, and this is minus 1 by 2 sigma square summation 2 into xi minus A into -1. Okay, this is the derivative we are getting, and when we equate it to 0, okay, when we equate it to 0, we are getting that n by sigma square x bar minus A is equal to 0. So n by sigma square x bar is equal to n by sigma square A. When we cancel, we get, okay, so we get no. Here we are getting that this is x bar and x bar minus A, and we know that x bar is an unbiased estimator, so you can take that expectation will be x bar minus A will be 0. So it almost x bar you can approximately take it as, okay. So here we get x bar minus A into minus n by sigma square as the double derivative. Sorry, this is single derivative. When we differentiate it with respect to A again, okay, this becomes minus n by x square. This inside derivative becomes -1. So minus in minus, it becomes minus in plus, it becomes minus. So in this way, we have obtained the variance of A cap is greater than or equal to sigma square. So with this, I'd like to conclude my lecture, and in the next lecture, we'll meet with one more important concept from 5th module. Thank you all.
Like, share and subscribe. Hit the bell icon for more updates.